This is the first video on Chapter 35, Related Rates. And again, when you look at your Chapter 35 from the notes, you're going to notice there are no definitions, no theorems, only examples. This is because you already know how to do these problems, you just might not know that you know how to do them. And so I'm going to do several examples of related rate questions. The idea is you're going to write an equation with the different variables in it. What variables you have depends on what problem you have. And you want to find the rate of change of one of these variables. And you're given information about the variables, you're sometimes given information about the rate of change of the other variables, but you're trying to find the rate of change of one of these variables. Okay, two pieces of advice. When possible, draw a picture. So when we look at example 275, we have a very classic example. We have a 15-foot ladder that's leaning against a wall and it's sliding down the wall. As it slides down the wall, y decreases and x increases. We're given the rate of change of y. We want to find the rate of change of x at a certain point in time. That is our problem. Now, the thing about your picture is do not put constants in the picture for things that are changing. I put a 15 right here. This is the length of the ladder. The length of the ladder isn't changing. The height the ladder is off the floor, this is changing. Now we're given at some point in time it's 9, but it is always changing. So I did not put a 9 in the picture, I put a variable because this is changing. Same thing with the x. At the point in time when y is 9, x is 12. But I do not put those in the picture. I put these in as variables because they're changing. That helps us get the equation right. The hardest part typically about a related rate question is writing this equation. Working with the equation once you have it is usually less difficult than finding the equation in the first place. This is usually the hardest step in a related rate problem right here. For this particular example, not so much, but when we get to the harder examples, you're going to see finding this equation is usually the hardest part. So, here it's just a matter of using the Pythagorean theorem. X squared plus y squared is equal to 15 squared. Now, the related rate part. We want to find the rate of change of x. So what we're going to do is we're going to take the derivative with respect to t of both sides. What is t? It stands for time. So we're going to find the derivative with respect to time of both sides. Now, x is a function of time, y is a function of time. We don't actually have them expressed as functions of time explicitly, so we're using implicit differentiation here. So we take the derivative with respect to time of both sides. The derivative of x squared is 2x times dx dt. So we use the chain rule. The derivative of x squared is 2x dx dt. The derivative of y squared is 2y dy dt. The derivative of a constant is always 0. So now that we've used implicit differentiation, we have 4 variables right here. We have an x, a y, a dx dt, and a dy dt. Now we look at the problem. And in the problem, we have to have been given the value of these variables or enough information to find the value of 3 of these variables. We're looking for dx dt. So the x, the y, the dy dt either have to be given or we have to have been given enough information to find those first. Okay, so we have x is 12. How do we know x is 12? Because when we look at the problem, we're told we want to find the rate of change of x at the point when y is 9. So if y is 9, again we use the Pythagorean theorem, this is a 3, 4, 5 right triangle, so we have 9, 12, 15. So x is 12. dx dt is what we're being asked to find. We're not going to find this in the problem. The 9 we were given. Now, we were also given dy dt. We were given the rate of change of y with respect to time. that it's sliding down the wall at a rate of 1 foot per second. Y is decreasing, right? As the ladder comes down the wall, y is getting smaller. So the rate of change of y is negative. So dy dt is -1, not +1. So now we just have a linear equation of dx dt. So we're going to solve for dx dt. It's 3/4. That means x is changing at a rate of 3/4 feet per second. So as the ladder goes down the wall, this ladder slides away from the wall at a rate of 3/4 feet per second. Now we'll look at example 276. We're throwing a rock into a lake. It creates a circular ripple. We're given the rate of change of the area, and we're being asked for the rate of change of the radius. You can draw a circle if you want to, but that's not going to be nearly as useful as when we did example 275 and we drew the triangle. So you can draw a circle here if you want to, but the picture isn't incredibly useful, so I did not bother with the picture for example 276. We don't need a picture to write the equation of the circle. So area is pi r squared. Differentiate both sides with respect to time. So here we just have dA dt. It's a derivative of the area with respect to time. We'll take the derivative of the right side with respect to time. So here we have dA dt. Here we have 2 pi r dr dt. Now we have three variables. We have dA dt, r, and dr dt. We're being asked for dr dt. So there needs to be enough information in the problem to know what r and dA dt are. We were given that dA dt is pi. So the area is expanding at pi square inches per second. And we were given the radius is 4. That is part of the problem. You'll notice for both of these, I did not talk too much about the information given in the problem. So I talk about that when we need it. You don't actually need to know what r is and what dA dt is to write this equation. So we write the equation, we take the derivative with respect to time, and now that we're looking for dr dt, now it's time to substitute. So dA dt is pi, r is given to us as 4. So now we solve for dr dt. We just have a constant equal to a constant times dr dt. So dr dt is 1/8. That means the radius is increasing at a rate of 1 inches per second.